imagine for a moment you're an engineer, maybe staring at a blank blueprint for a brand new railway bridge.
Hmm.
Or perhaps it's a big station building, one that's going to serve millions of people. How do you even start deciding how safe it needs to be?
That's the fundamental question, isn't it?
Exactly. Where's that line between, safe enough and maybe over-engineered, especially when you've got lives, huge costs, and the whole transport network potentially on the line?
Right.
So today we're diving deep into exactly that, how engineers figure out those critical safety benchmarks. They're often called reliability goals for the massive structures that basically form the backbone of our
Yeah,
railways.
the civil engineering side of things.
Precisely. We're going to try and untangle how safety here isn't just like avoiding failure completely.
No, that's not really feasible, or even the goal sometimes.
Right. It's more about finding a smart balance, isn't it? Between the risk, the potential consequences, and, well, the money involved.
The economics, yeah, it always comes back to that eventually.
So we'll classify these structures, understand the different kinds of risks, and then really dig into the financial calculations behind making things incredibly safe.
And we're focusing specifically on the civil structures today. The bridges, the tunnels, station buildings.
Not the trains themselves or the signaling systems. That's a whole other deep dive.
Exactly, just the big physical infrastructure.
Okay, let's unpack this. So, starting point. How do engineers even begin to classify these massive structures to set those safety goals? What's the first step?
Well, the very first thing is just understanding what kind of structure it is. Broadly, you have things like track-carrying structures.
Okay, that sounds obvious enough. Bridges, viaducts.
Exactly, the things actually holding the tracks up. And then you have ancillary structures, that's sort of everything else. Tunnels, station buildings, platforms, retaining walls.
Got it. So type is one thing, and I guess how long it's supposed to last matters too. Like a small rural station isn't built to the same standard as a, say, major cross-country bridge.
Absolutely not. The intended design working life is a huge classifier. That station building you mentioned, maybe designed for 50 years, something like that.
Okay.
But a major bridge or maybe a long tunnel under a river, you're aiming for 100 years, minimum, sometimes much longer. The investment and the implications are just on a different scale.
Okay, and this is where I think it gets really critical. You mentioned structures are also classified by the potential consequences if they fail. Consequence classes, or CCs, right?
That's right, CCs. This is probably the most important classification for setting reliability targets.
So how does that work? How do you decide, say, this bridge is CC2, but that tunnel is CC4? Is it always clear cut?
It's defined, but applying it takes judgment. You have to think about the ripple effect of a failure. So at the low end, you've got CC1, minor impact.
Okay, what does minor mean here? Like a shed falling over?
Sort of, yeah. Predominantly insignificant material damage, maybe a small secondary building at a station. If it fails, it's an inconvenience, maybe some local cost, but no real public safety crisis, no major disruption.
Right, so CC1 is minor. Then CC2 starts to involve actual tangible consequences, maybe injuries or bigger disruptions.
Exactly. CC2 involves material damage, definitely functionality losses for the railway operator, but the societal impact is still pretty limited.
Okay.
Any environmental damage, if there is any, could probably be fixed in weeks. And yes, crucially, the expected number of fatalities would be low, generally less than 5.
And examples, like a bridge on a quiet branch line.
That's a good example, yeah. Or maybe a standard station building on a regular line.
Yeah.
Some delays, some cost, but not widespread chaos.
Okay, then we step up again to CC3.
Yes, CC3. Now we're talking about societal significance. Material and functionality losses are bigger, and you'd expect regional disruptions.
Regional, so if affecting a whole area for a while.
Potentially, yeah. Vital services might be impacted for several weeks. Environmental damage might be more serious, but still relatively contained. And the potential human cost here is higher, possibly up to 50 fatalities.
Wow, okay, so quite a jump.
It is. Many structures that are important regionally, but maybe not critical national lifelines, would fall into CC3.
And then CC4 sounds like it's getting into disaster territory.
It is. CC4 is classed as disastrous events. Severe losses of societal services, national-level disruptions lasting months, potentially.
Right. Okay.
Significant environmental damage could spread further, taking a long time to clean up, and the potential fatalities jump again, up to 500.
Goodness, what kind of structures are we talking about here?
Critical assets.
Right.
Major bridges on main lines, all tunnels on major lines typically fall here, key buildings at the biggest, busiest stations, things the country relies on.
And is there a CC5?
There is CC5, catastrophic.
Yeah.
But thankfully, it's very uncommon for railway structures.
Mm.
We're talking disruptions beyond national scale, lasting years, widespread long-term environmental damage, more than 500 fatalities, just the absolute worst-case scenario.
Let's hope we don't see many of those.
Absolutely. The aim is always to prevent getting anywhere near that.
So the basic principle seems simple enough. The bigger the potential mess if it fails.
The higher the reliability we demand.
Yep.
Exactly. You build in a safety margin proportional to what's at stake.
Okay, so we've got these consequence classes. We understand the scale of potential disaster.
Yeah.
That brings us to, well, how do we actually define reliability? Because you said it's not about zero failures.
Right. That's key. Reliability in engineering, especially civil engineering, isn't this black and white, it will never fail idea. That's just not realistic.
So what is it then?
It's about accepting that failures can happen, albeit very, very rarely for well-designed structures. Our focus is on managing the probability or the frequency of those failures down to acceptable levels, incredibly low levels.
So you design for a tiny admitted chance of failure within the structure's life.
Precisely. A small calculated risk.
And I know there's a distinction made between different types of risk, individual versus group risk. How does that play into setting these reliability levels?
That's a really important distinction, yeah. Individual risk looks at the danger to any single person.
Like my risk walking through that station.
Exactly. It focuses on making sure no single individual is exposed to an unacceptable risk over time. Often, the benchmark is something tiny, like a 1 in a million chance per year.
Okay.
But for railway structures, where people usually only spend a short time passing through a station, crossing a bridge on a train, individual risk is often less critical than the other type.
Which is group risk.
Yes, group risk. This is hugely important for railways. It's about preventing accidents that cause multiple fatalities or large-scale harm all at once.
Because a bridge collapse or a tunnel fire could affect hundreds of people.
Exactly. Society has a much lower tolerance, you could say an aversion, to events that cause widespread disaster compared to scattered individual incidents, even if the total number of fatalities over time were the same. So group risk really drives the reliability targets for major structures.
And engineers have tools to visualize this group risk, don't they? I've heard of FN curves.
Yes, FN curves are a standard tool. They plot the frequency of accidents against the number N of fatalities.
So it gives you a picture of how often different scales of accidents are predicted to happen.
Exactly. You plot the expected performance of your structure or system on this graph, and you compare it to lines representing acceptable risk levels. If your curve stays below the acceptable line, especially for high-end events,
High fatalities.
then you're generally okay. If it creeps above, especially at the high consequence end, that's a big red flag. It needs addressing.
It makes the abstract idea of risk much more concrete.
It does, and it directly connects to societal values about preventing large-scale tragedies. This is also where the LRPO principle comes in.
Yes, ALAR. As low as reasonably practicable.
That always sounds sensible, but potentially debatable.
It can be. ALAR defines this middle ground. There's a level of risk that's clearly unacceptable and a level that's broadly acceptable. In between is the ALARP region.
Well, you have to reduce the risk further.
You have to reduce it, yes, unless the cost and difficulty of doing so are grossly disproportionate to the safety benefit gained. And grossly disproportionate sounds like where the arguments might start.
That's often the case. It forces a very explicit discussion about cost versus safety, about societal values. How much are we willing to spend to prevent a very rare event? It's rarely a simple formula.
So it's not just pure calculation.
No, there's judgment involved. But what's interesting in railways is that we also look at history.
How so?
Well, the industry has actually derived some of its risk acceptance criteria by looking at historical safety levels. The thinking is, if the safety record of traditional railways is generally seen as acceptable by society.
Which, compared to other transport modes, it often is.
Exactly.
Yeah.
Then we can use that performance as a kind of benchmark for new designs or assessments.
So you look at how often accidents of different severities have happened in the past.
Right. For example, statistically, events with medium consequences, let's say 1 to 10 fatalities, might have had an annual probability around 1 in a billion per train kilometer historically on well-run networks.
1 in a billion per train kilometer. That is incredibly low.
It is. And when you translate that into return periods for specific structures, the numbers become astronomical.
Return periods. You mean how often we'd expect an accident of that scale?
Yeah. So take a busy 50-kilometer railway tunnel. An accident with those medium consequences, 1 10 fatalities. The acceptable return period might be calculated at around 300 years.
Okay, 300 years still feels quite frequent if you're the one running the railway.
Well, remember, that's for that specific tunnel. Across an entire network, the numbers work out. But look what happens when consequences get worse. Severe consequences, maybe 11 to 100 fatality.
The return period goes up.
Jumps to maybe 3,000 years for that same tunnel. And catastrophic events, 101 to 1,000 fatalities. You could be looking at 30,000 years.
30,000 years. Okay, that puts it in perspective. We're designing things to withstand risks on geological timescales almost.
That's the level of safety we aim for with critical infrastructure, yes.
Yeah.
It shows how seriously group risk is taken.
Now, obviously, human safety is the top priority, but you mentioned reliability goals also factor in economic and environmental risks.
Absolutely, they have to. Economic risk includes the obvious direct costs, repairs, replacement if something fails,
Right.
but also the indirect costs, which can be massive. Lost production or business disruption because the line is closed, costs of rescue operations, maybe relocation expenses, legal fees, and importantly, damage to the organization's reputation.
Which can be hard to quantify, but very real.
Very real. You can actually develop FD curves, similar to FN curves, where D is the economic damage in monetary terms. So we plot frequency against cost.
Interesting. And environmental risk, how do you measure that?
That looks at permanent or long-term damage, harming sensitive habitats, polluting water sources. The damage level can sometimes be defined by the estimated recovery time.
So, like, minor damage might recover in 6 months, but serious damage could take 20 years or more.
Exactly. It tries to put a scale on the ecological impact. Now, combining all three human lives, economic cost, environmental damage into a single decision-making framework, that's complex.
I can imagine. Different units, different values?
It's incredibly challenging. But the goal is to make informed, holistic decisions, considering all these facets.
Okay, so we're managing probabilities considering consequences. You mentioned engineers often use a reliability index, beta, instead of just talking about failure probability. Why beta?
Good question. Beta, the reliability index, is mathematically linked directly to the probability of failure. But it's often, let's say, more convenient, especially when dealing with the very, very small probabilities we aim for in structural safety.
How so?
Well, instead of saying the probability of failure is 0.00000001, you might say the target beta index is, say, 4.75. It's just a different scale, derived from the normal distribution in statistics. A higher beta means higher reliability, lower probability of failure.
So it's a standardized score. Easier to compare different designs or standards.
Exactly. It gives engineers a common language and a more manageable number to work with for setting design targets. But it's crucial to remember these are formal target values used in design populations. They aren't necessarily predicting the actual frequency of failures in the real world, which is influenced by many factors beyond the initial design. They are benchmarks for design adequacy.
Got it. So let's talk about the economics again. You said the core objective is minimizing the total cost over the structure's life.
That's the ideal, yes, from a purely economic standpoint. And that total cost has several components.
Okay, what are they?
First, the initial cost. Designing it, building it, surveys, materials, construction, everything up front.
Makes sense.
Second, the ongoing costs. Inspections, monitoring, routine maintenance, minor repairs, keeping it performing as intended over decades.
Right, the upkeep.
And third, critically, the expected costs related to failure. This is where the probability and consequences come back in. Is the probability of failure multiplied by the cost of that failure.
Including all those things we just discussed, repairs, downtime, compensation, cleanup.
Exactly. All those potential future costs, weighted by how likely they are to occur.
So engineers are playing with a decision parameter, maybe how strong a beam is?
Could be, yeah. Or the quality of the concrete, the depth of the foundations, something they can control in the design.
And making that parameter better, stronger, stiffer, whatever usually costs more upfront.
Typically, yes. Higher initial structural cost.
But it lowers the probability of failure and therefore lowers that third chunk of the cost, the expected failure cost.
Precisely. So you're looking for the sweet spot. The point where the total cost initial plus maintenance plus expected failure cost is minimized over the structure's whole life.
It's an optimization problem.
It absolutely is. A complex one.
And for things like railways that last potentially 100 years or more, how does the timing of those costs factor in? Money today isn't worth the same as money in 50 years.
You hit on a crucial point. The discount rate.
Okay, what's that?
It's an economic tool to account for the time value of money. Basically, a cost incurred far in the future is considered less burdensome in today's terms than the same cost incurred right now.
Because you could invest that money today and have it grow,
That's the idea. So a higher discount rate gives less weight to future costs, like potential failure costs decades down the line.
which could mean.
It could theoretically favor designs with lower initial costs, even if they might have slightly higher maintenance or failure risks further out.
Hmm.
Choosing the discount rate is actually a very significant decision in these long-term infrastructure projects. It reflects assumptions about future economic growth, inflation, and investment returns.
Wow, okay. So economic policy can directly influence engineering safety decisions.
Indirectly, yes, through things like the chosen discount rate for public projects. It's a complex interplay.
And what about putting a value on human life in these economic models? That sounds difficult. Is that where the life quality index or LQI comes in?
Yes, the LQI is one approach that tries to address that very difficult issue. It attempts to establish a relationship between wealth, life expectancy, and the time available for leisure or productive activity.
So it tries to put a monetary value on preventing a fatality.
Essentially, yes, based on how much society implicitly seems willing to invest in measures that extend life expectancy or improve quality of life. It helps weigh the cost of safety measures against the value of the lives potentially saved, trying to bridge the economic and ethical dimensions.
Is it widely used?
It's a recognized methodology, often used in socioeconomic cost-benefit analysis for major public safety decisions, like in transport or health. It's not without its critics or complexities, but it provides a framework for making those incredibly tough trade-offs more explicit.
Let's make this concrete again. Imagine we're optimizing, say, a railway bridge. How might these economic calculations play out depending on the consequence class?
Okay, good example. Let's say the bridge failure would have considerable consequences, maybe our CC2 class. Material damage, some disruption, low chance of fatalities. If you run the numbers, optimizing purely for minimum total economic cost might lead you to a target reliability level, a beta value. It's actually pretty close to what current standard design codes already require.
So for CC2, the economics roughly align with existing standards.
Often, yes.
Yeah.
But now consider a structure with very great consequences, maybe CC3. Regional disruption, potential for dozens of fatalities.
Right.
Here, purely economic optimization might actually push you towards designing for a higher reliability level, a higher beta, than the minimum required by standard codes.
Really? So it's economically better to be safer than the code demands?
In many cases for high consequence structures, yes. The potential cost of failure is just so enormous economically, socially, reputationally, that spending a bit more upfront to significantly reduce that failure probability turns out to be the cheaper option in the long run when you factor in the expected cost of failure.
So that's a huge takeaway. For
Mhm.
new structures, especially important ones, economic optimization often pushes us beyond the minimum safety requirements.
That's often the finding, yes. Building an extra safety upfront can be the most economically rational strategy.
Now, what about structures that are already there? Old bridges, existing tunnels. You can't just apply the same standards as for a new build, can you?
No, absolutely not. It's a fundamentally different situation, mainly because the cost of improving safety is usually much, much higher.
Retrofitting is expensive.
Extremely expensive. Think about strengthening an old bridge while keeping trains running, or upgrading a tunnel built a century ago. The costs of these safety measures can be astronomical compared to incorporating them into a new design from scratch.
So does that mean we accept lower safety levels for existing structures?
Not necessarily lower absolute safety, but the target reliability level used for assessment might be different. For existing structures, the minimum acceptable level often becomes dictated purely by human safety requirements, that absolute floor we talked about, rather than by economic optimization.
Because the cost to reach the economically optimal level might be prohibitive?
Exactly. The cost-benefit calculation changes dramatically. So, for existing structures, minimum human safety levels often become the decisive factor, whereas for new structures, economic optimization frequently drives the targets higher.
So when you assess an old bridge, you might actually have two different targets in mind.
That's a common approach, yes. You need two levels. First, a minimum level. If the structure falls below this, it's deemed unsafe, and action repair, strengthening, maybe even closure is mandatory. This level is typically set based on ensuring basic human safety, meeting those group risk criteria we discussed.
Okay, the absolute must-fix level.
Right. Then second, you might define an optimum upgrade level. This is the target you'd aim for if you do decide to upgrade. representing the most economically efficient way to improve the structure's reliability, maybe bringing it closer to the standards for new designs, but acknowledging the higher costs involved.
So you wouldn't necessarily upgrade it all the way to a new standard unless it was economically justified.
Precisely. You might aim for a significant improvement, but perhaps not the absolute highest theoretical optimum if the cost is truly excessive.
And studies actually show this difference, right? The minimum acceptable beta for an existing structure can be lower than for a new one.
Yes, analyses often show that the minimum acceptable reliability index for assessment can be lower, sometimes significantly lower, than the target for a new design, reflecting that massive difference in the cost of achieving safety improvements.
Okay, this is fascinating. Let's try one more specific example. How does this all apply to something like deciding how far away a bridge pier should be from the railway track? That seems like a classic risk trade-off,
It is. It's a great example of balancing competing factors. The risk here is a derailed train hitting the pier.
which could be catastrophic.
Absolutely. So the further you place the pier laterally from the track, the lower the probability of a collision, and thus the lower the potential consequences, economic damage, train damage, potential injuries, or fatalities.
But moving the pier further away means,
It means you need a longer bridge span to cross over the tracks. And longer spans generally mean a more substantial and therefore more expensive bridge structure.
so cost goes up as risk goes down. The classic trade-off.
Exactly. You're balancing the increasing cost of the bridge structure against the decreasing expected failure consequences.
And how does train speed play into this? I imagine faster trains make it trickier.
Hugely significant. Studies optimizing this pier distance show a dramatic effect.
Hmm.
For, say, conventional speeds like 120 or maybe 160 kilometers per hour,
Okay.
the economically optimal distance for the pier might work out to be around 3 meters or so from the track center line.
3 meters doesn't sound like much.
So, well, that's the economic optimum in that
Yeah.
scenario. But watch what happens with high speed. If the train speed goes up to 230 kilometers per hour,
Yeah.
that optimal distance jumps significantly, maybe to around 9 meters.
Wow, triples it. And for even higher speeds, like 300 kilometers.
Then you could be looking at needing over 15 meters of lateral clearance for the pier to be economically optimal. The potential impact, energy, and derailment dynamics change drastically with speed.
15 meters. That requires a completely different type of bridge design.
It certainly does. Much longer spans, much higher costs. But here's the crucial final check.
What's that?
Even after you find that economically optimal distance, say 9 meters for the 230-kilometer train, you must check if it meets the minimum human safety criteria, those FN curves or equivalent grouped risk limits.
And sometimes it might not.
It's possible. In some high-speed scenarios, even the economically optimal pier distance might still result in a residual risk to passengers that exceeds acceptable societal limits.
So what happens then? You can't just build it at the economic optimum if it's not safe enough.
Absolutely not. Human safety is the non-negotiable floor. If the check fails, further measures are required. You might have to increase the pier distance beyond the economic optimum, accepting the higher construction cost. Or you might look at other mitigation measures, perhaps installing robust crash barriers near the pier, or implementing specific track design features in that location to reduce derailment risk. But you have to bring the human safety risk down to an acceptable level.
So economics helps find an efficient solution, but safety provides the absolute boundary condition.
That's a perfect way to put it.
Well, there you have it. We've really gone deep into this, haven't we? Setting reliability goals for these huge railway structures.
It's a complex field.
Absolutely. We've seen how engineers classify structures by consequence, the difference between individual and group risk, and how safety, economics, and even environmental impact all get weighed in the balance.
And that crucial difference between designing something brand new versus assessing something that's been standing for decades.
Right, and how often the most economical solution for new builds is actually safer than the bare minimum required. And always, always, that human safety aspect is the ultimate deciding factor.
It truly is a fascinating interplay of engineering, economics, and societal values. This complex dance between risk, cost, and safety underpins the infrastructure we rely on every day.
So, thinking about all this, consider those vast railway networks crisscrossing the globe. Knowing the depth of thought that goes into their safety, what questions does this raise for you, our listeners, about the future? Especially as technology like AI advances, as materials get smarter, and maybe as our own understanding and tolerance of risk continue to evolve. What trade-offs do you think will become even more critical in the decades ahead?
That's definitely something to ponder. How will we balance innovation with these fundamental safety principles in the future?